Our first speaker lunch features Dr. Saurish Das from LAM. Dr. Saurish Das, a computational expert with a PhD in computational modeling from Eindhoven University of Technology, specializes in multiphysics modeling, numerical methods, and fluid dynamics. Over a decade of industrial experience at organizations like Shell and Ansel, he is currently a staff engineer at LAM Research, where he leads multi-physics modeling efforts to tackle complex engineering challenges. His work uses advanced simulation methods like fluids, thermal, electromagnetic, and structural applications in high-tech industries. Today, Dr. Das will discuss boiling-based. Welcome.
Good afternoon, everyone. And this is the last presentation before lunch. And I will try to finish in 25 minutes.
Yeah.
30 minutes.
25.
Oh, 25, and you can then ask me a lot of questions during the lunch time. And thanks for serving for inviting me here. And as you see, today I will discuss about the boiling-based cooling system. So far, we have seen application of boiling space industries by ISRO, and also lot of application in terms of chip cooling. But here we try to discuss about the chip manufacturing, the fabrication of the chip. About my company, LAM Research, it's a semiconductor company. And I like this slide very much, this plot. Basically, it shows how the semiconductor industry is growing for the last 30 years, starting from 1980, when we had our first personal computer. Then moving to the era of HPC, high performance computing, mobile devices, and now it is keep on growing, miniaturing the storage, compute power. And now we are in 20 last decade we are working on for different applications, starting from wearable to micro devices, IoT, lot of sensor. And LAM is actually wafer fabrication equipment manufacturing company. So whatever we see in the chip we use, it actually passes through any of our reactor. So if you see a working, okay,
Won't show that.
okay, if you see any PC or say any mobile device, and if you go into deep, then you will see the microchips, and in the chips it is a complex connection of different wires, and our equipment actually manufacture those devices. So I divide this agenda into three parts. First, I will discuss a bit about the IC fabrication fundamental. So it will give us the problem statement, why we apply the boiling-based cooling system. Second is the semi-realistic wall boiling model. So this will provide us the model to design the some of the challenges, and then we will marry the first and two to actually use this model to apply for the boiling-based cooling system. And question answer during the lunch time. So first part is the IC fabrication fundamentals. Just I would like to give you the brief of the length scale. So again, mobile device in centimeter length scale. Then go to the chip device, chip level. It is a millimeter length scale, and all the LAM people are smiling because they have seen this slide several times. And in the millimeter length scale, you can see the single chip, which is a kind of size of a coin, 23 millimeter, 5 rupees coin. And the next step, if you go even deeper, this is a micrometer scale, where actually it consists of 3D structure of logic unit. And if you also compare this with the here of a human hair, which is of 5 micrometer in length scale. And then if you go to next level, which is the 3 nanometer or 4 nanometer technology, which is nanometer scale, and if you consider human DNA, it is of 10 nanometer. And now today's all the transistor we use in specifically in Apple or in any of this Intel or NVIDIA processor, it is of 3 to 4 nanometer technology. So we are manufacturing the size of the transistor which is smaller than a human DNA, and we try to do by the macroscopic change of the flow and thermal analysis. Okay, and if we think about any semiconductor or any circuit, it consists of three parts, right? It needs a load, the resistance or resistor. We need a conducting wire, which is can be copper and aluminum, and we need insulator because we need to insulate the aluminum. Similarly, if you see inside the chip, we have first silicon, then we can dope it either with P-type or the N-type doping. Then we need the insulating layer. So typically we react oxygen or nitrogen or carbon dioxide to make silicon oxide, silicon nitride, silicon carbide. That's provide the insulating layer or dielectric layer. And then from the P-type and N-type silicon, we need to connect with the real world. So for that we need a conductor layer. And in conductor layer we use typically copper, tungsten or molybdenum based on the application to application. So again the chip, integrated chip, a single piece of die that if you remember our old days, we use this piece into our motherboard. A lot of pins are there. Then if you cut, we get this cross section of the logical chip, and if you can see from bottom to the top, so we have the base as a substrate silicon wafer, while we first do the doping for P-type and N-type, then it goes in the upward direction with a lot of interconnects of lot of trielectric layer copper connection, and then it goes to the solder bump, and this solder bump is actually connected to our motherboard of the PC, and it is the kind of connecting from the silicon world to the actual physical world. And this is the one FinFET transistor that we studied probably during our college days on or high school days. So in today's device, almost it takes a billions of this transistor and connect it in a complex network, and so that it can interact with each other and do the number crunching and storing the memory. And just to show you the how this copper interconnects work. And manufacturing of this chip. So whoever actually work in a microfluidics device, so it is very similar. Actually, microfluidics device actually adapted some of these techniques for fabrication. So we add material, create pattern for masking, remove material, and we repeat. So first, notched wafer comes into the fab. Then this is the portfolio of lamp. So in the blank wafer, first we deposit the thin film, then photoresist. Patterning and lithography not done by us, and then it goes to the next step of etch, because after you do the lithography, then we need to remove some of this material to make the pattern, and then we strip, and then there's a lot of contamination, we clean, and then again we deposit, and we keep on repeating this process, and we draw perpendicular to the wafer to create this layer, and we create in a 300 millimeter wafer, we create this pattern, and next we cut this each of this pattern, and that makes our one of the chip. Of course, we need to do a lot of testing, and also packaging is another portfolio for lamp, where one of these chips is actually getting connected to the motherboard. Earlier we used to use copper pins, but nowadays this packaging also use the same techniques but in a much larger scale. So these scales are typically in the nanometer scale, but packaging is done in a micrometer scale. And Lam Research is the market leader in several of this manufacturing and packaging industry. And actually, if you see a lot of news about the India semiconductor mission, so mostly we're focusing on the packaging industry because it is less sophisticated, I must say, because it's use the same techniques, but it is not a nanometer scale, mostly at a micrometer scale. And there are a few challenges, and slowly I'm going to the problem statement. There are a few challenges in nano world. One is that so we see the two distinct steps. One is the deposition of the material and etching, the removal of the material. So first is that if you want to drill pretty narrow, high aspect ratio holes to the wafer through the dielectric, there's always a challenge. I will come to that later part, because nowadays all our chips are actually we are 3D integrated, because as we cannot spread It's like any metro city. As we cannot go in the vertical direction, we move to the horizontal direction, we move to the vertical direction. And just to give you the so now this technology is almost 1:100. It's a bit old slide, 1:100 aspect ratio. And just to give you a sense that in Burj Khalifa, the tallest, one of the tallest building, it has a 9:1 aspect ratio. But now our technology is almost 100:1 aspect ratio. And there's always a challenge how we manufacture. And of course, there's a for the deposition step, there's also a challenge that if we keep on shrinking the dimension, so this is typically called the critical dimension of CD, then there's always issue of the pinch off. And to solve that, we have the option that we do the atomic layer deposition. So it's a self-limiting reaction where single atoms actually react with the silicon or any other deposits and create a single layer of atoms, single atomic layer. But still we have the problem or the challenge for the high aspect ratio etching. And if you go to the etch process, just to give you the screen inside of the reactor, then we have the process gas coming in, we have the RF power at the top, we hold the wafer in the pedestal, or that is the that I will come to later, and then we create a high plasma to actually do the this etching process. And if you see the etch process, that this actually we use different gas, so fluorine is one of them, and say we want to etch is silicon dioxide. So this fluorine comes, it react with SiA2, create SiF4 and oxygen. Both of them are gaseous phase, and it goes away from the system. But also we need to use plasma, because in earlier days we used to use only the chemical etching process, like we have talked about in the previous presentation, that this chemical etching is one of the process to create the pattern. But in the nano world, if we use only the chemical etching without the plasma, the challenge is that it will not only go deeper, also it try to spread out the hole size that you can see in this portion. So to do that, to avoid that, what we do, we create accelerate, we create a RF field which accelerates the fluorine ion, which is or fluorine radical, which is perpendicular to the wafer. So it can hit this surface, which will have a highest etch rate. But at the same time, when it goes through these stages of high aspect ratio, it tries to also pulse the side walls. And what is the solution? One of the solution is that we make this thing ultra low temperature. So of course RF field accelerates the F plus ion perpendicular to the wafer, and silicon sidewise damage is due to the random motion of the gas molecules. So if we make this to the cryo temperature, what will happen? We will reduce the random vibration of the molecules or the atom, so that it only accelerate perpendicular to the wafer, and at the same time we can make these ions as a chemically inert, so that it will not react with the side wall of the these trenches. And if I show you some of this typical same image that you can clearly see, maybe I can show it here. So you can clearly see this is almost 2 to 3 nanometer of dimension. You can clearly see this bulging effect, and we develop a lot of process and lot of sequence how we can avoid these things and go deeper. But definitely we need to go for a very low temperature. And I mentioned you that how we deliver this low temperature to the wafer. We use electrostatic chuck, so it's a kind of wafer holder in which this wafer sits, and so it has also a coolant channel. And now you can understand why I am going in this coolant channel will start the boiling. And it also, between the wafer and the ceramic, we supply the helium gas. Why we use the helium gas? Because helium has a very high thermal conductivity. So we want to reduce the thermal resistance as much as possible between the wafer and the ceramic. Now this this whole system acts in a vacuum chamber, and now if we supply say 40 to 50 torr of say helium pressure. So 1 atmospheric pressure is almost 760 torr. So you can just do a simple calculation and you can calculate that this wafer will experience almost 50 to 60 kgs of upward force, which tries to fly up the wafer. And we need something to hold this thing back. And wafer is a very thin element, right? It is less than a 1 millimeter of thickness. So we use some clamping electrodes which supplies DC voltage with a DC voltage and create the electrostatic force, which tries to hold back the wafer towards the ceramics, towards this electrostatic charge. That's why it's called the electrostatic charge. And at the same time, we have the plasma, which increases the wafer temperature. We have this. We discuss about the helium backside pressure, DC power for the embedded electrode to pull the wafer back, and cryogenic coolant, which passes through this coolant channel. So this provides us the problem statement. So we start about the challenges for the nano world. We start with that we want to have a very low temperature. We want to maintain a very low temperature. At the same time, it's a 300 millimeter wafer, and we want this temperature to be very uniform throughout this whole wafer. Otherwise, we will lose the performance of some of the chip. And so we want to develop a device which can provide the ultra low temperature, and at the same time, it has a temperature uniformity around 300 millimeter of the wafer. And as you can imagine that if you go for a very nanoscale features, that temperature uniformity we try to achieve is less than almost 0.5 degree or 1 degree centigrade, and that is actually boiling can help. Then I will briefly discuss about the semi-mechanistic wall boiling model, which I developed during my time at ANSYS. So it is not a very sophisticated model, I must say, but it works wonderfully. Even several different coolant channel and several different coolant application. So what it does that it solves the CFD. In the CFD grid, it solves the mass, momentum, and energy equation, and it solves the K omega turbulence model because though the boiling heat transfer is high, but still we want to capture the single phase heat transfer, and also we want to capture the phase fraction. For that, we use the mixture multiphase model. So as you can see in this equation, and so this is the equation for the mixture multiphase model. So where it in a compression cell, if you have some bubbles, it actually homogenizes the bubble in a homogeneous property, and we use the mass, momentum, and energy equation using this homogeneous property. So and also it has some source and sink term, that is this m dot L to B and m dot V to L. So based on the temperature and the compression cells, it add the source term for conversion from liquid to vapor, or if it is temperature goes below saturation temperature, it also revert back the vapor into the liquid phase. And probably it's the 10th time we're seeing this curve. And so in the model, what I've shown, so we captured all the single phase flow phenomena. At the same time, it captures the phase change phenomena while it converts the liquid to vapor or vapor to liquid. But at the same time, when there's nucleate boiling, there's a theory that due to the microconvection because the enhancement of the roughness of the wall area, the heat transfer coefficient also increases apart from the latent heat part. So in this model, what we have done, that we divide the total heat first into this is a typical semi-mechanistic mechanistic wall boiling model, into the convective part and the nucleate boiling part. For the convective part, we use the turbulent model, which is available inside the solver, and for the nucleate boiling part, we use the empirical correlation. Again, this empirical correlation, like we discussed, is the 30 to 40% inaccurate, but most of the cases I found that in this application, still it is working, maybe reasonably good. And I chose change correlation because apart from the pool boiling correlation, Rosenov correlation, there is this S term, which is actually represent the suppression of the nucleate boiling. As you can see, it is function of Reynolds number. If Reynolds number tends to 0, then S become 1. So it's a completely full boiling correlation. But if the high Reynolds number, it actually suppresses the boiling. That is also experimentally found that it reduces the formation of bubble, and this actually will capture the for different flows and for unique vaporization for different channel configuration. And we have validated this model for 50% ethylene glycol, and as you can see, for this three curve for the three different velocities, 0.25 meter per second, 0.5 meter per second, and 1 meter per second. As we increase the velocity, the single phase curve is actually shifting. So that indicates that we have the enhancement, we have the increase in the heat transfer coefficient. The slope of this curve is increasing, and at the same time, this three color represents for different pressure, and after the onset of boiling, we can clearly see that it captures the nucleate boiling phenomena quite well, at least in a macroscopic scale. And this is the only one setup validation I'm showing, but we have validated for different fluids and different configuration and different channel height, and it is very reasonable to see that this correlation or this solver which we develop, so adapting the 1D correlation 3D environment predicts quite well for different different boiling nuclear boiling regime for different coolant also. So now in the first part we have seen the problem statement. In the second part we have seen we have the boiling model. Now we like to utilize this boiling model for the designing the our ESC, designing the coolant channel to maintain the low temperature. So typically there's two approaches, right? I don't need to say it again, that one is sensible cooling and is a latent heat based cooling. Since sensible cooling, it is simplistic system and substitute system. We can use it low system pressure, so the heat transfer coefficient doesn't depend on the pressure of the system. But the challenge is that when you have a very high temperature, high heat flux, then it is based on the m dot Cp delta T. So there will be definitely a delta T variation. Otherwise, it cannot extract heat unless we use different coolant with Cp higher Cp, or we change the mass flow rate. But when you go for the cryogenic temperature, actually we have very small number of coolant that we can actually use for temperature like -6 to -100. And for the boiling based cooling system, the temperature is almost constant. That's the best part, that if the pressure is constant, the temperature variation is almost constant. Higher heat transfer rate, that we already have seen that it can extract more and more heat from the system without changing the much of the coolant temperature. But the challenge is that if my system pressure is varying, so my saturation temperature is varying along the cooling loop, and that actually changes the saturation temperature and creates the temperature non-uniformity. Another challenge for this particular problem, the vapor stratification, that we have this pedestal or the wafer holder, heat come from the top section, and flow is happening there. But as heat come from the top section, there's always chance for the stratification happens. So some vapor will always form, and if the velocity is very low, then vapor sticks and we can go to this critical haze region very easily. And we need to use very high pressure. Okay, going there. So this is just to show, demonstrate this application. So this is the typical ESC looks like. It is embedded in a aluminum surface, and this is just a dummy coolant channel. So we have lot of IPs, and due to configuration, I cannot show the actual system, but it is a very simplistic design because this component has lot of other connections. So we cannot actually make this very simple design because it needs to be passed through lot of turns, and that makes our life very difficult for this maintaining the temperature. And we use coolant as a -100 degrees centigrade. So it is enters into the system at a subcooled region, take the heat, so you see some boiling, and it try to maintain the exit at a quality of 20%, not more than that. Otherwise, we might get some issues with this cryo situation, and we use 5 kilowatt of heat load. That's a huge heat load we see for the almost 0.0 meter square of the area, and we use 10 lpm flow rates. So this is some of the simulation results for temperature map, and of course we see some of the vapor stratification this model captures, and by changing the flow rate and by changing the design, we can actually avoid some of this vapor stratification. And another part of this model that we use the real gas properties from the NIST database, real thermodynamics data, and as a result, any pressure variation in the system, we can actually calculate what is the saturation temperature variation. And as you can see, this is a very simplistic channel. We have only pressure variation of 0.1 bar from the inlet to outlet, and saturation temperature variation less than 1 degree centigrade. So that is a good. And here actually try to compare the sensible and boiling. Of course, I don't need to glorify it again. That in the boiling based cooling system, we can actually extract more and more heat, and but at the same time in our application, temperature uniformity is very important. We can see that temperature non-uniformity is almost 10 degrees centigrade for the single phase coolant, and if we go for same for the boiling based cooling system, it is almost 5 degrees centigrade. So we have a huge benefit for going to the boiling based cooling system. Of course, in real life, the temperature non-uniformity is less than 1 degree or even 0.5 degree centigrade. But as this channel is not a real one, it's just a dummy to demonstrate the modeling approach or the design thoughts we use, we can see the 5 degree centigrade of the variation. Yeah, so the last slide, the takeaway message. I try to guide you through the different IC fabrication process and its challenge, how the macroscopic results actually helping to get the nanoscale critical dimension properly. I demonstrate the use of semi-managed wall boiling model for the wafer temperature control and for designing. Of course, nuclear boiling helps for temperature non-uniformity, that is more important than the heat transfer rate. And also, I try to show you how we were driving the next generation technology by one atomic layer at a time. And this is one of the very interesting read recently published in our website, introducing LAMP Cryo 3.0. So you can also read in later times to see how this cryo technology is helping for this nano fabrication or highest pressure fabrication. Thank you.
Thank you, Dr. I request Professor Peter Stephen.